In the last class, we have discussed the general equations that can be applied to any interaction and how to represent them diagrammatically using Feynman diagrams. We have also discussed how to calculate the combinatorial factors for each Feynman diagram. And today's class, we'll see that there is a better way to do this. Okay. For nth order perturbation, for nth order perturbation, there will be 1 by n factorial when you expand the exponential. So you can see this is second order perturbation, and for any second order perturbation you will have a 1 by 2 factorial present there. Also, there will be n interacting vertices which can be permuted in n factorial ways. If you see, there will be, this is a second order perturbation and there are two vertices here. In each diagram you can see there will be two vertices. So here you have one vertex, here there is another vertex. So there are two interacting vertex. Even in this diagram you can see there are two interacting vertices. Therefore, for any n interacting vertices, you can have n factorial ways for permuting these vertices, right? And these two will get cancelled, which is known as the modulo symmetries in permuting vertices. So these two cancel the modular symmetries in permuting vertices. For each vertex, minus I lambda by 4 factorial 5 to the power 4. Okay, if each phi in this 5 raised to 4 contracts differently, then permutation of 4 phi's will be 4 factorial. Therefore, the two 4 factorials again cancel the modular symmetries in permuting vertices coming from the same vertex. Forget about the 1 by n factorial from exponential and treat each vertex as minus I lambda, right? Forget about the 1 by n factorial factor coming from the exponential and treat each vertex, each interacting vertex as minus I lambda. Okay. But this way leads to overcount, and therefore we have to divide by symmetry factors from permuting vertices and legs. So in the first diagram, the vertices x and y are not symmetric, right? So in this first diagram you can see the vertices x and y are not symmetric, but the vertex coming from x, there are two symmetric legs. So there is no symmetry associated with permuting vertices. Similarly, vertex from y has two symmetric legs. So these are the two symmetric legs for the vertex y, and these are the two symmetric legs for the vertex x. Right? Therefore, we have to divide 2 times by 2 factorial. Similarly, in the second diagram, the vertices x and y are not symmetric, okay, because x is connected to x1 and y is connected to x2. So we cannot say that they are symmetric. X and y, the vertices x and y are not symmetric, but between x and y there are 3 symmetric legs which can be interchanged. So this is one symmetric leg, this is one symmetric leg, this is another symmetric leg. So there are 3 symmetric legs which can be interchanged, and therefore we have to divide by 3 factorial. So these rules for writing down the expressions from diagrams are called the Feynman rules. These are known as Feynman rules. So the first Feynman rule says that each external point is associated with a line. For example, in this figure, x1 and x2 are the external points, and you can see that each external point is associated with a line, right? Each external point is associated with a line. So if you have x1 as an external point, then it is always associated with a line. For each propagator, okay, it has two endpoints. Correspondingly, you can write down a GF for each propagator so you have an internal point, another internal point, and this is a propagator. Okay, so propagator has two endpoints, and correspondingly we can write down the Feynman function for a propagator. So that is the second rule. Third rule says that for each vertex, so how do you define a vertex? Where the interaction happens, right? So for each vertex at x, you can associate a factor minus I lambda integral d for x. Okay, so wherever there is a vertex, you can always associate minus I lambda integral d for x with the vertex. Fine. And fourth one is the last step, which says that divide by symmetry factors for diagram. So the last step is to divide by symmetry factors. So from each diagram, by applying these rules, we can obtain the analytical expression. Okay. So I'll just give you an example. For example, let's consider the second diagram. Okay. So this is the easier diagram. So if you consider this second diagram, the symmetric factor is 3 factorial, because we have already discussed that the vertex is not symmetric. Vertex x and vertex y, they are not symmetric because x is connected to x1 and y is connected to x2. Therefore, it is not symmetric. But they have 3 symmetric legs. Right? The vertex x and y have 3 symmetric legs, and therefore the symmetric factor is 3 factorial. Okay, the symmetric factor is 3 factorial here. So let's, I'll draw it once again here. So I have a point x1, external point, then x and y are the internal points, and x2 is another external point, and here I have a propagator, right? And number of symmetric legs is 3, right? Therefore, symmetric factor associated with this diagram is 3 factorial. Okay. Now, the second Feynman rule, let's say, the third Feynman rule. So, the fourth rule says that you have to divide by symmetric factors. So, the symmetric factors associated with diagram is 3 factorial. So, I have to divide by 3 factorial. Okay, let me do that at the last. So, what is the next Feynman rule? It says that next Feynman rule is for each vertex x, you can associate minus I lambda d4x, integral d4x. So, here there are 2 vertices. So, with the vertex x, I can associate I lambda integral d4x, and for the vertex y, I can associate I lambda integral d4y, right? And for each propagator, we associate Feynman function gf0. So there are 3 propagators here, therefore I have to associate with gf0 x minus y raised to 3, because there are 3 propagators, right? And I have to divide by the symmetric factor 3 factorial. Okay. So therefore, the expression associated with this diagram will be minus I lambda, right? Minus I lambda whole square. So there is a minus here. There is a minus here. So minus I lambda whole square integral d4x integral d4y gf x minus y divided by 3 factorial. This is the analytical expression corresponding to the Feynman diagram. This diagram. Okay. So these are the Feynman rules in coordinate space. We can also have it in momentum space. Okay. So these are Feynman rules in coordinate space. We can also have it in momentum space. So let's see. Next topic that I'll be discussing is the Feynman diagrams in momentum space. Okay. Suppose we have endpoint correlation function, okay, in standard Fourier transform. So the Fourier transform of the endpoint correlation function, right, is equal to the Fourier transform of the endpoint correlation function is given by integral d4x up to d4xn e raised to I p1 x1 e raised to minus I pn xn gn of x1 xn. So from translational symmetry of the Hamiltonian, we expect that the momentum is conserved. So if the momentum is conserved, then I can write this as 2 pi to the power 4 Dirac delta in 4 dimension P1 up to Pn Gn of P1 up to Pn. So this is the Fourier transform of the endpoint function in coordinate space to the endpoint function in the momentum space. In translational symmetry, there is a freedom to subtract all the coordinates by taking a point as a reference. That is Gn of x1 up to xn. This is the endpoint function in the coordinate space, can be written as G x1 minus xn x2 minus xn up to 0. So when you plug this equation for Fourier transform, then you get a delta function, right? In momentum space, the Feynman propagator is given by Gf of k is equal to minus I by k square plus m square minus I epsilon, right? So this is a propagator with k, momentum k. So at each vertex, for example, you have a vertex x, right? Then, and these vertex are arising from an external point, for example y1, y2, y3 and y4, right? Then you can always associate a momentum, for example k1, k2, k3, k4. Okay, so at each vertex we have an integration d4x. So here gf of 0 x minus y1, then gf 0 x minus y2, gf 0 x minus y3, and there is one more leg gf 0 x minus y4, right? So this is in coordinate space. So I can transform each of these Feynman function into momentum space. Okay, so you'll get integral. So this is for this one, first Feynman function. Okay, gf of x minus y1 will become integral d4 k1 e raised to I k1 x minus y1 gf k1. Similarly, I can write for the other Feynman functions also, right? So I can write d4 k2 e raised to I k2 x minus y2 gf of k2. Similarly, d4 k3 e raised to I k3 x minus y3, then gf 0 of k3. Similarly, I can Fourier transform the last term gf of x minus y4 into the momentum space. So that will be d4 k4 e raised to I k4 x minus y4 gf of k4, right? And we know that this is proportional to 2 pi to the power 4 Dirac delta in 4 dimension k1 plus k2 plus k3 plus K4. So momentum is conserved at each vertex, right? It does not matter what the y1, y2, y3, y4, etc. are. It can be external or internal points, but at each vertex momentum is conserved. So what are the rules to compute the endpoint function in the momentum space? Rules to compute the endpoint function in the momentum space. Each external point can be associated with a factor 1. Okay? Each external point can be associated with a factor 1. So if you have an external point like this, you can always associate it with a factor 1. Okay? For each propagator, you have a factor minus I by p square plus m square minus I epsilon. So for each propagator, you have a factor minus I by p square plus m square minus I epsilon. And the third rule says that each vertex each vertex there is a minus I lambda, right? Then impose momentum conservation. Impose momentum conservation. While doing the Fourier transform, each propagator will have a momentum integration because each one of them has a momentum integration. If you did not understand this point, just see this expression. While doing the Fourier transform, each propagator will have a momentum integration, right? Similarly, the second propagator also has a momentum integration because each one of them has a momentum integration, and some of them can be cancelled while imposing momentum conservation, and the leftover ones have to be integrated over each undetermined momentum. Okay, so the fourth step will be you have to always integrate the leftover undetermined momentum. So I write d4pi by 2 pi to the power 4. And the final step is to divide by the symmetry factor. Divide by the symmetric factor. So symmetry factor is Same in coordinate as well as momentum space. So once you find the symmetric factor, then it can be used in both the spaces. Now let's take an example. Okay. In coordinate space, I have x1, it's an external point, then x, y, x2, right? Then I can have something like this. Now the same diagram in momentum space, it will be right, P1, P2, K1, K2, K3. Okay, the direction of momentum can be assigned as per our choice. So at this stage we don't. P1 is equal to, so you can see that at this junction P1 can be written as K1 plus K2 plus K3, and in the other junction you can write P2 is equal to minus K1 minus K2 minus K3. So this is minus of K1 plus K2 plus K3, which is equal to minus of, what is K1 plus K2 plus K3? It is P1. So P2 is equal to minus P1. Then in this diagram I can actually rewrite the notations. For example, if I have something like this, so instead of P2, right here it was P2. So P2 is equal to minus P1. So minus in the sense the direction has to be reversed. So I can write P2 as something like this. So let me write P2 is equal to minus P1 is equal to P, right? And similarly I can write P1 as P. Then this will be K1, this will be K2, and K3 also I can rewrite as P minus K1 minus K2, right? P minus K1 minus K2. Fine. Now for this diagram I have to write the expression. So for each vertex I have to associate minus I lambda. So there are two vertices here, interacting vertices. So I lambda square. And here there are, how many undetermined momentums are there? There are two, K1 and K2, right? So I can write integral d4 K1 by 2 pi to the power 4, then d4 K2 by 2 pi to the power 4. So these are the undetermined momentum. Undetermined and this is coming from the two vertices. Now I have to write three propagators. Okay, I have three propagators. First one is minus I by k1 plus m square minus I epsilon, and the next propagator is k2. So how do I write the propagator for k2? Minus I by k2 square plus m square minus I epsilon. Then the third propagator will be minus I by, so instead of k3 I can write p minus, right, p minus k1 minus k2 minus I by, instead of k3 I can write p minus k1 minus k2 whole square, right, plus m square minus I epsilon. This can be in one bracket. Okay, now there are two external factors, right? There are two external factors which I have to write minus I by p square plus m square minus I epsilon. So there are two such things, therefore I write square. These are the two external factors. Right? Now the whole thing divided by the symmetry factors. The whole thing divided by the symmetry factor 3 factorial. So this is the expression for this Feynman diagram in momentum space. Let's also recall that in interacting theory, the endpoint function is given by Gn xn is equal to the vacuum state in interacting theory time ordering of phi of x1 up to phi of xn okay, and we have considered this to be x bar, and we can also write in terms of the vacuum in scalar field theory, which is time ordering of x bar e raised to I si divided by time ordering of e raised to ISI. After expanding the power series, the mth order perturbation in the numerator becomes I raised to m by m factorial time ordering of x bar will be there, then Si m times, and in the denominator I raised to m by m factorial zero time ordering of Si. There will be m of them, okay. So this can be computed using Wick's theorem, but we go for Feynman diagram and analytical expressions. Any diagram contributing to the numerator of endpoint function has n external legs with m vertices. So you have to be very careful here, because any diagram contributing to the numerator, okay, of this endpoint function. So this is an endpoint function, and in the numerator will have n external legs. N external legs with m vertices. Now diagrams corresponding to the denominator will have no external legs because there are no phi's there. Okay, so this is for numerator. Right? So for numerator, n external legs with m vertices. For denominator, there will be no external legs as there are no phi's present there, and therefore they are called the vacuum diagrams. Okay. Therefore I can say that the term 0 time ordering of e raised to ISI can be used to calculate the vacuum energy of the interacting theory. So this can be used to calculate the vacuum energy of the interacting theory. Okay, so for today's class we'll stop here and we'll continue in the next class.